Two force members are portions of a structure or complete structures, but they would have only forces applied at 2 points on the member. And if it's in equilibrium, those two forces must be equal, opposite, and collinear. So let's draw a little random object here. If I were to apply a force here, in order for this to be in equilibrium, I have to have an equal and opposite force in that direction. In other words, they have to be equal, opposite, and it doesn't really matter what the shape is. If the shape is like this, if I have a force that is pulling in this direction, then the only way for this to be in equilibrium is to have another force pulling equal and opposite with the same magnitude, or equal, I guess that means the same magnitude. It has to be equal, opposite, and collinear like that. So the shape doesn't matter. It can be any shape. However, most of the time with two force members, we're talking about links or cables. But again, they can be structural members with some other shape. They have to be pin connected at both ends. In other words, there's no resistance to moment. The line of action obviously is the same of both ends. If they're lined up in collinear, that means the line of action of this one, which goes this way, is going to be the same as that one. Alright, a couple of examples. If we have a string and I'm pulling it with a force, then I obviously have to pull it with the same force back there. That is now a two-force member. I could have a link that is going in this direction with some force. In order for it to be in equilibrium, I have to put an equal opposite force like that. I could be in tension as well. It doesn't really matter if it's a link in tension or compression. However, if I had something going this way on this one, and then I had another force on this end going this way, that does not work. It would have obviously some ability or some tendency to rotate. The other thing that doesn't work is if I were to push on it with both of them. Even if they're equal and collinear, if they're not opposite, in other words, this, if I put both theirs, clearly it's going to be moving. So that one doesn't work as well. Now, shape doesn't matter. I've already talked about this bent link a little bit, but this is an example in your textbook where you're pulling on this sort of thing and it's got this bent link. So look at that and you can see how this is a two-force member because it goes like that. Let's look at this one. If I'm pulling on this guy, is this one a two-force member? Well, no, it is not a two-force member because, first of all, it's not pin connected on this end, and the line of action of these 2 points is not lined up. This is the line of action here, and it doesn't go through that point. So just by the fact that it doesn't have the line of action going through the other support means that it can't be a two-force member. And the other reason it can't be a two-force member is because it's not pin supported there. So this is a fixed support, not a two-force member. A couple of things we know about two-force members. If I'm pulling at one end, obviously it's going to be pulling at the other end, and a couple of things are going to be similar here. If there's an angle associated with this angle theta, then that's going to be the same angle theta there. If there is and that's also going to be the same as the line of action right there, which is also angle theta. If you have a component over here, I'll say that there's going to be we'll call this A, we'll call that AX, and then there's going to be BX over here. If this is going to be B, and if there's going to be a B here, or A here, AY, this is going to be BY. And what we can say is that AX is equal to A cos theta, which is also equal to BX, which is equal to B cos theta. We know that AY is equal to BY. And we know that all the thetas are equal to each other. So when you see a two-force member, it's pretty handy to recognize that these are going to be equal to each other and these are going to be equal to each other, and they have the same angle to relate. Alright, so let's talk about three force members. I want you to just refer you to this piece in your textbook. This is not a major portion of the course, but it is actually kind of useful that where you have three forces, if that two force member is there and then the support here, whatever the reaction and direction of the resultant and direction of that reaction, they all line up to a point. And so you should look at that and understand three force members. All right, let's look at how we draw free body diagrams with two force members in here. Often when we're trying to resolve something, we're either looking for the force in the two force member, or maybe we're looking at the force in the reaction at one of those points. But let's just understand. If I were to draw the free body diagram of the vertical part, which is kind of what we generally do, I'll go ahead and draw that in there. I understand that because this is a two force member, all the forces have to line up. Because I'm pulling it in this direction, I know that it is going to be in tension. So I'm going to say that this has a tension coming back like that. It's going to have some force here, and it's going to have a y and an ax. If I were to draw the free body diagram of that two force member, because I know it's in tension, it's going to be pulling like that, and it'll be pulling on both sides of that. So if you will, this is going to be point D, this is B, and this is also going to be point B. Alright, how about if the two force member is at an angle, which is the general case where you have to do a little more work. We'll draw again the free body diagram of the vertical part. It has that, and it has a reaction. Call that AY and AX. Let's look at the two force member. If I'm pulling it going in this direction, it's going to be in tension, which means it's pulling down. So I'm going to draw that force pulling down like this. This will be BD. This is force BD. And if I draw the two force member, it will have the same kind of thing. It'll be in tension, going like that, where this is force D or point D and this is point B. Whatever the angle is here is going to be the same as the angle right up there. That angle is going to be the same. And when we see that, it's very helpful to understand that the components of the force, whatever this cosine component and sine components are, then those are going to be the cosine and sine components on the two force member up there. Well, here are two problems, two pictures that look pretty similar, but they are fundamentally different, and I just want to talk a little bit about how we approach these things. This is a beam, and we probably are looking for some reaction at A. That's often the question. Or maybe we're looking for the force in the supporting structure. But you can see what's happening. There's a pin here. It's going to rotate this way, except that this little strut here, this thing here, is trying to keep it from rotating. It's probably pretty obvious, but this is going to be in tension. It's pulling back. This one over here obviously has a pin. Here's our beam, and we would, if we wanted to find the reaction at A, we should recognize that this beam, or this link here, is in compression, pushing back up. So we handle them in a similar way, but it's important to recognize, if you can, tension or compression. You'll make a lot fewer mistakes if you can recognize that tension or compression at the beginning of the problem, and then put the forces in the way they're supposed to be from the beginning. So let's solve this. Let's solve this first one over here. Let's draw the beam. Has something going down. It actually has this little knot sticking up, so I'm going to draw it like that with the tension member going up like that. And then over here I'll have my A, Y, and AX. All right, let's say that we're looking for the components of the reaction at A. This is 8 kilonewtons here. And in order for us to solve anything about A, I need to know what the tension is here in this beam. So let's draw our two force components. It has a component going this way and a force going in this direction. And this is a 3, 4, 5 triangle, so this will be the 3/5 of T, and this one will be the 4/5 of T, going like that. All right, so let's sum the moments about A equals 0. The reason I'm doing that is I can solve for this tension in one equation, because I know that, and I know all the lever arms, I can solve for the tension in one equation if I sum the moments about A. If I sum the moments about any other point, I'd have both of those variables as unknowns. So in this case, it is fastest to sum the moments about A to get started. So I'll say that this is going to be 3/5 of t and it has a lever arm. The lever arm is 7 meters. In other words, it is this whole thing here. This 4/5 t also has a little lever arm, and you can see how it is up here. It looks like it is 0.4. It's pretty small, but it's still considered, and then it's going in the same direction. So I'll say 4/5 of t, and it has a lever arm of 0.4. Then I have the 8 kilonewtons going in the negative direction. That'll be times 3, and that's equal to 0. So I can solve that for the tension is equal to 5.31 kilonewtons. All right, now that I do that, it's pretty easy then to solve for the others. And I'll move that up just a little bit. And yeah, I think that's all we need to have. Well, let's see, there we go. Some of the forces in the x direction. Go to the x. Sum of the forces in the x is equal to 0. And here I have positive ax minus 4/5 of t equals 0. And I've solved that for t, so I can say that ax is equal to 4.25. And then sum of the forces in the y is equal to 0. So I've got ay minus 8 plus 3/5 of t. Again, I've already solved for t, so I can solve for ay here is equal to 4.82. And those are the last two pieces of my unknowns. So generally it's pretty straightforward, especially when you know an angle. And that's kind of what we're dealing here with these two force members. The angle is given here in terms of this ratio. So if that's given, then that's the way we set that up, is as a percentage of t or a proportion going in the particular direction. Let's look at this other problem, and you can see. Okay, this next one, what we're going to do is recognize that similar kind of beam, but in this case, because it's trying to push it down this way and it rotates about this point, I can pretty much guess that C, this link here, is in compression. So let's draw it like that and make sure that we know how to draw the free body diagram. So I'm just going to do that. And then I have that 4 coming down. Here, because that two-force member is in compression, I'm going to draw it like this. I'll call that DC. Now, it has some angle associated with it. Because this is 1.5 on this side, 1.5 on that side, this being under a right triangle, I know that that internal angle is 45 degrees. So let's go ahead and do that. So that's 45, which means that now I have two components. I'll say that this one is the sine component. I'll call this DC. I'll call this the cosine component. And this one then will be DC sine component, or sine 45. Now, what about the reaction over here at A? Again, I don't know for sure the directions, but I'm going to guess that AY is going down and that AX is going in that direction. And so when I do my moments and forces, we'll find out if I drew that arrow incorrectly. So let's go ahead and sum the moments about point A to start with. Now, why am I summing the moments about point A? This is easiest because there are two unknowns at A. There's one unknown here. So if I sum the moments about this point, I can solve for the unknown with one equation. So that's pretty easy to do. So sum of the moments about A. I have the DC sine component times this lever arm going in this direction. That's positive. And that lever arm is 1.5. Minus 4 times this lever arm going in this direction, which is negative. And then I can solve for DC of 11.3. So with one equation, I can solve for the force in that two-force member. How about the forces AX and AY? Let's sum the forces in the X and sum the forces in the Y and see what we get. So sum of the forces in the x direction. Again, I assumed AX was going in the negative direction. Positive DC cosine 45. I've already solved for DC. DC cos 45 right there. And then I can solve for AX is equal to 8 kilonewtons. Now this is, I can also call this component CX if I wanted to. That is CX going that way and CY going that way. But what I want you to recognize is that if I'm looking for the force here, that force CX is actually DC cos 45. So when I do that, I find that AX is equal to 8 kilonewtons. And if I sum the forces in the y, I assumed AY is going negative, so that is negative in my equation. DC, I've assumed this is going in the positive direction, so DC sine 45 going positive. And I still have that negative 4 going down, and I can solve that for AY is equal to 4. Anyway, so there's your introduction on two force members, let's see where we're at. Well, we have one more concept I wanted to visit with you about here, is that these two problems look very similar, but they are different, and I just want us to understand and see the differences. If I were to push this with a 4 kilonewtons and I got this at some angle, it's going to have two forces kind of pushing it in this direction or trying to rotate it in this direction. If that's the case, then this force here, this two force member here, is going to be in tension, which means it's trying to be pulling backward like that. Over here, in this case, I have that same 4 kilonewton force here. This one is a pulling force instead of a pushing force, but it's still trying to push it in this direction. In this case, this one will be in compression, and it'll have a component going in this direction and a component in this direction. So what I want to do is draw the free body diagrams and then just talk about them for just a few minutes. Okay, so I have drawn the free body diagram over here, and I got the vertical force, or the vertical member that I care about. It's going to have this X component here and a Y component. It's going to have that 4 kilonewtons. This is the tension member here, so it's going to have that component pushing back that, or pulling back that way. So if I would just look at the forces in the X direction, I'd have those three forces which we can compute. If I look at over here on this side, I have the same component as here because it's the same angle. It doesn't really matter if it's a pushing force or a pulling force, those are going to be the same. So this component in the X direction is going to be the same as that. It still has that pushing force pushing there, that 4 kilonewtons. On this side, because it is in compression, it's going to have that force pushing back. So if I look at the forces in the X direction, it is this one, and this one, and this one, and that's the same as these. So again, because these dimensions are all the same, I think we could conclude that AX here is equal to AX over here. How about AY? AY is going to have this component down. Because this is in compression or tension, it's going to have this component down. And AY is going to be pulling up like that. Over here, this has got the same pulling down, except that this one has because it's in compression, it's going to be pushing up. So in the Y direction, it's got this one force going down, this one's going up. So clearly AY is going to be smaller on this side and larger on this side. So in this case, AX does not equal AY does not equal AY on that side. So anyway, sometimes you can just by observation see those things, and I just wanted to point that out because that might be useful as we solve problems together.